So
Ah, wow. Yeah, I think. And how is it? Is it effective immediately, or you need to wait for some time?
I think you need to wait 2 weeks. Yeah.
Oh, so that's basically the whole time. It covers the full time of the Congress.
No,
right?
but you know that Russians have been flying to the United States to get Johnson and Johnson, so that after now so that they can enter the States in the future, because Sputnik V.
But there are different strategies. I had a friend who flew to Germany, and there he got a kind of fake vaccination by Germans. Yeah, I think Johnson and Johnson is very good because you only need one fake.
Only one.
One fake vaccination.
That's it.
That's right. So.
Oh, my friend, it was not fake. He had a fever for 2 days. Yeah.
Yeah. Oh, I think there was some famous story that some people came and they wanted a fake vaccination, and the doctor who was administering kind of actually gave them the real one, pretending it was a fake one. So they sued him. And I think they all went to whatever jail, or were all fined. All participants of this operation, of course, the doctor for agreeing to do a fake vaccination for money, and then them for paying for a fake vaccination. So, yeah. All right. So I think we should probably start. Let me search for the title. So today it's a great pleasure to have Sam Evans as our speaker, and he will be speaking on the variety of coisotropic subalgebras. Sam, I give you the floor.
Okay, thanks. Thank you to the organizers for the opportunity to speak. And I feel like, when I listen to the seminar, I usually feel like people are talking about much more exciting things than what I'll talk about. So I apologize in advance for talking about something a bit archaic. So I want to talk about a problem that I've been working on sort of gradually with my students over time. So this is the problem of understanding the coisotropic Lie subalgebras of complex semisimple Lie algebra with the standard bialgebra structure. So just to formalize things, we take the group G with the standard Poisson structure pi G. So G is a complex semisimple Lie group, and pi G is the standard Poisson Lie group structure given by difference between left and right translation of an R matrix. And small g is Lie algebra, and it's a Lie bialgebra. So in particular, the dual G star is a Lie algebra. And then for C and G, a Lie subalgebra. I want to let C naught be the elements in the dual, which are perpendicular to C, or just the annihilator of C and G star. And then one says that if C is a Lie subalgebra of G, then C naught is sorry, I did these in a hurry last night. Then C is coisotropic if its annihilator is a Lie subalgebra of the dual. So I learned about this notion from a paper by Marco Zambon, and I'll say a little bit more about what Marco did in a moment, later in the talk. But today I want to present some ideas and results on this problem due to Nicole Kroeger, and more recently to Doan and myself in So these are students of mine and this is what they wrote their PhD on. So the main idea is to restate the problem in terms of Lagrangian subalgebras. So let's recall that the double, which I'll call D of G, is isomorphic to G plus G. And the triple D together with the diagonal and a subalgebra G star is a Manin triple, which corresponds to this Lie bialgebra. So G sub delta is just the diagonal copy of G. And if we fix a triangular decomposition of our complex semisimple Lie algebra G, so G is n minus plus t plus n, with T a Cartan subalgebra, and the sum of the positive root spaces and n minus the sum of the negative root spaces, then G star is the anti-diagonal of the Cartan plus n minus. And we can consider the invariant non-degenerate symmetric bilinear form on D, which is given by the difference between the killing forms on the two factors. And then we let L of D be the subalgebras L in the Grassmannian, such that L is isotropic with respect to this symmetric bilinear form. And L is a Lie subalgebra. So this is, because the form is non-degenerate, this means that L is maximal isotropic as a subspace. So if we were doing this with respect to a symplectic form, everybody would understand that it should be called a Lagrangian subalgebra. But the term is borrowed in this case, in the symmetric case also. So anyway, L of D is called the variety of Lagrangian subalgebras. And Lou and I introduced it and studied it in a couple of papers from the 2000s. Okay, so there's some easy results which relate coisotropic subalgebras to Lagrangian subalgebras. And these are things that Nicole Kroeger proved in her thesis. So if C is coisotropic, then C plus C naught is Lagrangian. This is basically formal once you have the idea of checking it. And then for C coisotropic, we'll let L of C be C plus C naught, so the associated Lagrangian subalgebra. And conversely, if L is Lagrangian, then L arises from a coisotropic subalgebra if and only if, as a subspace, L splits as L intersect the diagonal copy of G plus L intersect G star. Okay, so like I said, so I hesitate a little bit to call this a proposition because, again, basically once you have the idea of saying this, it's completely routine to check. Okay, so let's let CL of D be the Lagrangian subalgebras associated to coisotropic subalgebras. So the L of C such that C is coisotropic. And then the map from coisotropic subalgebras to to its image is bijective. And then so the reason behind doing this is that the set of coisotropic subalgebras is closed inside the variety of Lagrangian subalgebras. And the variety of Lagrangian subalgebras is a well understood algebraic variety. So we can describe its irreducible components completely. They're all smooth. We know essentially how they intersect. All right, so let's, just for convenience, I want to assume that the center of G is trivial and let capital T be a maximal torus of G with Lie algebra T. And then we take the diagonal copy of T, of the torus T. So this diagonal copy of the torus is the intersection between the normalizer of G in the group D, which I think maybe I forgot to define, but it'll be G cross G, with the normalizer of G star and D. So what that implies is that the diagonal torus is the biggest subgroup acting on the variety of the variety CL of D. So CL of D is a closed T diagonal stable subvariety of the variety of Lagrangian subalgebras. All right, so the approach we're taking to try to understand what the coisotropic subalgebras is that the variety L of D is a well understood Poisson variety. And we want to use this to understand the coisotropic subalgebras. Great. Are there any questions? Okay, so some motivation for doing this. So there's a degeneration L0 of the variety of Lagrangian subalgebras. So this essentially arises by degenerating the standard Poisson structure on G to 0 just by scalar multiplication. So if we give the group G the 0 Poisson structure, then G with the 0 Poisson structure is trivially a Poisson Lie group. Its double is the semi-direct sum Lie algebra of G with G dual. And G dual here is abelian. Now, understanding the Lagrangian subalgebras of D0 so this is a wild problem. It would involve understanding all the Lie algebras of a semisimple Lie algebra, which is one of the linear algebra problems that's known to be essentially intractable. But the limit, you can take the limit as T goes to 0 of L, you can degenerate the doubles D to this degenerate version D0 through a family, and you can take the limit of the Lagrangian subalgebras, and this limit should be more tractable. So here, dt is the Lie bialgebra associated to G with a scaled version of the standard Poisson structure. And one can write it down explicitly. If we identify D with D0 as vector spaces in the obvious way, so in the sense that both are transparently can be identified with G plus G star in a transparent manner, then the coisotropic subalgebras are essentially the points in the variety of Lagrangian subalgebras that don't change when we degenerate. So basically what I'm saying is that I would be very interested in understanding this limit, and the coisotropic subalgebras are a part of it, which would be easy to understand. Okay, as part of her thesis, Doan computed the coisotropic subalgebras in the case of SL2. So I want to describe the answer. In the case where the Lie algebra G is SL2C, the variety of Lagrangian subalgebras has two connected components, which I'll call Z1 and Z2. So Z1 is the wonderful compactification of PSL2, and it can be realized as, so let me say this, so. And usually the wonderful compactification is not such a familiar variety, but in the case of PSL2, it's just the projectivization of 2x2 matrices. So it's identified with P3. There's another component, which I'll call Z2. And Z2 is isomorphic to P1 cross P1. We can embed P1 cross P1 into the projectivization of 2x2 matrices and realize it as when we do that, we can realize it as the projective classes of matrices with determinant 0. However, even though I'm describing these both in the same variety, in the variety of Lagrangian subalgebras, they're different connected components. So this P3 is different from this P1 cross P1, which is inside of P3. They're just in different places in the same variety. All right, so then we can compute explicitly the coisotropic points in each of them. So I'll write CL of ZI for the coisotropic points in ZI. So CL of Z1 is just the projectivization of the set of points with the lower right corner equal to 0. So that's a P2. And then there's also the class of the identity, which is a point. So this is G diagonal. And for example, this point is T diagonal plus n minus. And the coisotropic points in the second, in Z2, looks like just P1 union a point. So the P1 is realized as the determinant 0 matrices in the Lie algebra SL2. So altogether, the coisotropic points in L of D looks like P2 union P1 union 2 isolated points. So it would be nice to find some more general principle which explain this. All right. Now, another feature which we want to use is the fact that there's a Poisson structure on the variety of Lagrangian subalgebras. So if we letting again D be G cross G, so its Lie algebra is small d. So then the group D acts on L of D by just the adjoint action. This gives a map from D to vector fields on the variety of Lagrangian subalgebras. We can take its second exterior power. And then if we identify D with D star using the form, wedge 2 of D has a canonical bivector, which basically just comes from pairing D with D star and making it into a symplectic vector space, so that G and G star are isotropic, and the pairing is just given. And yeah, okay. And then we consider the bivector given by pushing forward 1/2 of the R matrix. And then what Lou and I proved many years ago is that the variety of Lagrangian subalgebras with this Poisson structure pi is a Poisson algebraic variety. So let's let G diagonal and G star be the connected subgroups corresponding to the pieces of the Manin triple. So then the G diagonal and G star orbits on L of D are Poisson submanifolds. This is something that was just part of the construction. And then by a theorem of Drinfeld, many Poisson homogeneous spaces of G and G star occur as G. Yeah, sorry, this is another mistake. So the reason why we started looking at this space was because it allows the study of Poisson homogeneous spaces and families. It gives one a possibility. It gives a mechanism by which one can understand how they degenerate. And that's how we originally started looking at it. So it played a family like this played an essential role in a paper we wrote, which interpreted some old results of Costant in terms of Poisson geometry. So then, of course, a natural question was to understand where the family really lived and the variety of Lagrangian subalgebras. So if L arises from a coisotropic subalgebra, so in other words, it's a direct sum of its intersections, then the Poisson structure vanishes at L. So in fact, there's a simple formula for the anchor map, which is just basically projection to the G factor, mod some subalgebra. And one uses this to derive the formula. And the converse, however, is false in general. However, in Lee's thesis, she understood that if the Lie algebra L is self-normalizing, then, so if the normalizer of L and D is equal to L, then the Poisson structure vanishing does imply that the Lie subalgebra arises from a coisotropic subalgebra. So the converse is true on certain kinds of Lagrangian subalgebras, which are at some level generic. So how do we use this? So let's suppose phi from G to G is an automorphism. And then we can let L sub phi be the graph of phi in G cross plus G, which is the double. So then the graph L sub phi is Lagrangian, which follows, it's essentially just the assertion that phi preserves the killing form. And also it's self-normalizing, which is essentially just an easy statement about symmetric spaces. So this follows from the fact that the normalizer in G plus G of G diagonal is itself. Okay, so our consequence of this is that if we take an automorphism phi of the Lie algebra G, then its graph L phi is coisotropic if and only if the Poisson structure vanishes at the point L phi. And so I should also say that the map from automorphisms to the variety of Lagrangian subalgebras that's induced from this. So automorphism phi goes to the graph is an open embedding, although it misses most of the irreducible components. Okay, so now the point of this is that we can take advantage of some work of Lu, which also connects to work with her students, K.Y. Chen and Simon Tao, and also work by some Italians working on algebraic groups, Cantarini, Carnovale, and Costantini. Sorry for my mispronunciation. So the question Lu answered is for which automorphisms of G the Poisson structure vanishes on a point L phi. She didn't say it precisely this way, but she does say that it's the same as this. So for this, I need to recall a definition. So a conjugacy class C and G is called spherical if it has an open orbit for the Borel subgroup. And I think it's implicit, but this means under conjugation.
Sam, sorry, maybe I don't quite understand the condition. So we're looking at the conjugacy class and we restrict the action to the B action. And there is a B orbit which is open in our conjugacy class?
Yes.
Okay, thank you.
So conjugacy classes with this property tend to be kind of small. You know, just so for example, if C were the conjugacy class of a regular semi-simple element in the torus, then the conjugacy class would look like G mod T, and Borel would just be too small to have an open orbit on that. So generally we're talking about small conjugacy classes, but it's not just the identity. So
but Sam, but then they would tend to be conjugacy classes of some unipotent elements, or some semi-simple elements may also have such a property, or
yeah, so I say this later down on the page, so let me just
okay, sorry.
say it now. So the spherical conjugacy classes are known for each simple group G. So for SL and C, they're either conjugacy classes through diagonal elements which have exactly 2 eigenvalues. So, you know, so these are quite singular, or they're conjugacy classes of the form scalar times the identity times a unipotent element with a Jordan type with with Jordan block decomposition with L copies of 2 and the rest just 1. So these are very small unipotent classes. So for example, at the level of the Lie algebra, I'd be talking about something like this. And at the level of the group, you just exponentiate it. You know, or you could have more of these 0, 1 blocks, but they're fairly small nilpotent orbits. Okay, so anyway, given a conjugacy class C, there always exists a unique element M sub C in the Weil group such that C meets the Bruja cell of MC in a set that's dense in C. And these MCs are completely calculated mostly in work by Lu and her students. So there's a theorem of Lu that says, this is the main theorem of her paper, that says the points in G for which the Poisson structure vanishes on L sub ad G are just the unions of C over the union over is just the disjoint union over the spherical conjugacy classes C of C intersect the sets B, MC, B minus. So these are not the Bruja cells. These are some kind of half opposite Bruja cells. So furthermore, each of these sets C intersect B, MC, B minus is a T conjugacy class. So is just a single orbit of T. So in other words, it looks like a torus mod some subgroup of the torus. Okay. So I'm not saying it because I think this is probably a bit on the technical side. So I didn't write it down because it seemed a bit too technical for a talk like this. But Lu also precisely determined when the Poisson structure vanishes on an L phi for any automorphism phi. There's an answer that's of the same nature as what I wrote down, but you have to look at some twisted conjugacy classes in order to say it. Okay, so anyway, that what this means is it completely settles the question of so I don't want to take a lot of credit for this, but basically it means that Lu settled the question of which L phi come from coisotropic subalgebras. Okay, and then we have some partial results on this problem in general. So the approach we want to take is that L of D has an action by T cross T, and the T diagonal action preserves the coisotropic set. So the idea would be to try to understand the fixed points of the T-diagonal action on the variety of Lagrangian subalgebras and describe the points in the coisotropic points, which are fixed by T-diagonal. So that, I think, is probably practical, and my student Sung Gao is working on that now, and he has some partial results. So that's a first step. And then the idea would be the idea which would be harder is that the T-diagonal action on L of D will give us a Belinsky-Berula decomposition of the variety. So roughly speaking, we decompose the variety L of D into attracting sets for each connected component Li of the fixed point locus. So the corresponding attracting set, which I would label by Li plus, is a vector bundle over Li, and the T-diagonal action will let us decompose Li plus into subbundles. And the question of whether something is coisotropic should be constant along the subbundles. So the idea is basically to try to use the toric structure, try to use the torus action to try to basically first answer this kind of question in easier cases, and then to try to use the corresponding structure to understand what's happening. So one can, you can phrase these ideas are at some level more theoretic, and you can phrase the Schubert cell decomposition of the flag variety in the same kind of language. And people answer questions about Schubert varieties using ideas like this all the time. So I think I said this earlier, but I should remark that L of D is singular. So singular varieties in general don't have a good Belinsky-Berula decomposition. However, its irreducible components are smooth. So this was something Lu and I proved many years ago. So we can apply the Belinsky-Berula decomposition component by component. Okay, so progress on this at this stage is kind of limited, but let me tell you what we've understood. So first of all, L of D has an irreducible component, which is G bar. So it's the wonderful compactification of G due to Dickinchini Procesi. And essentially what I'm saying is just we've embedded G into L of D by mapping an element G to the Lagrangian subalgebra LG. So I'll call this maybe I. And G bar is just I of G closure. So this is one of the ways that Dickinchini and Procesi realized the wonderful compactification. All right. Now it's fairly easy to describe the torus cross torus fixed points on G bar. So what you get is just a bunch of you get a bunch of points corresponding to, oh, sorry. You get a bunch of points corresponding to elements in the Weil group cross the Weil group. So the subtext for this is that G bar contains a closed d orbit, which is the flag variety cross the flag variety. And the T cross T fixed points in G bar are all in this closed subvariety. And of course, this is just given by pairs, it's easy in standard algebraic group theory to see that this is just pairs like this. Okay, and it's also easy to describe ZYW as a Lagrangian subalgebra. It's just representative of Y, representative of W, applied to the Lagrangian subalgebra, T diagonal plus n comma 0 plus 0 comma n minus. Okay, so then the question is, when is a point ZYW coisotropic? So this requires a little bit of Lie theory. So we just let phi y be the set of positive roots with the property that y inverse takes that root to a negative root. And then what Kroeger proved is that ZYW is coisotropic if and only if phi y intersect phi w is empty and y inverse w squared is the identity. So it's a, it's a nice, clean combinatorial criterion. So I should remark that Kroeger's result is a bit more general than this and should determine which points in just in the full variety of Lagrangian subalgebras that's fixed by T cross T are coisotropic. And secondly, the reason why we're led to this was by trying to generalize something that Marco had done, constructing coisotropic subalgebras using, I think he used, so this is a construction of, sorry, Zambon gave a construction of coisotropic subalgebras using a particular kind of long root. And what Nicole was trying to do was basically to generalize this. So she succeeded. All right. So last night I had one of these, I was having trouble sleeping and I had one of these moments I sometimes have where I was wondering if this result was really correct. So I tried to calculate what the coisotropic subalgebra that corresponds to a ZYW that satisfies the condition. And what you find is some part of the Cartan, and then some sum of negative roots, plus some sum of positive roots. And I had one of these moments that I sometimes get before talks where I panic and think that the result might be wrong. And but anyway, I actually was able to check that it really is a least subalgebra. I mean, it had been proved previously by other means, but it was reassuring to see it could be done by elementary means. Okay, and then I wanted to comment on a few things about this. So D has a finite number of orbits on G bar, which are indexed by subsets S of the simple roots. There's an open orbit, and there the coisotropic set is completely understood using Lu's results. There's a closed orbit, which is G mod B cross G mod B minus. In there, the coisotropic set is understood by Kroeger, at least on the T-diagonal fixed points. The general coisotropic, so the coisotropic set in the full variety, in the flag variety across the flag variety is not known yet. However, in her thesis, Doan has some results about on the coisotropic set in the other orbits. And this is expressed again in terms of root system data. So it's fairly clean, but it's kind of technical, as some of you who've tried working with parabolics and Levy subalgebras would know. So I won't, I didn't write it in these notes. And more recently, my student Song Gao has computed the T-diagonal fixed points on G bar. And it seems that it's definitely a union of closures of torus orbits. And it seems that it's even just a union of toric varieties. So what I want him to do is to compute the coisotropic locus in the T-diagonal fixed points on G bar, and then try to generalize this to the rest of L of D. Okay, so anyway, this is what I wanted to say. So thank you for your attention.
So thanks a lot. Any questions or comments? You can either unmute yourself or raise your electronic hand.
Anton, can I ask?
Sure.
So Sam, what did you say about the T-diagonal orbits on G bar? Sorry, I didn't get.
So you mean just at the end?
Yeah, at the end.
So it's not the T-diagonal orbits, it's the
Fixed points.
So it's the conjecture is that it's a union of toric varieties.
So on the
and
open
it's
part
almost certainly proved. So an example is that, so T-diagonal X on G bar by sorry, T-diagonal X on G just by conjugation by T.
Right.
So there's an obvious part here. So T and G is fixed by T-diagonal. But the fixed set is projective, so that means T bar is fixed by T-diagonal. T-bar is a very, so this is a toric variety. Its span is the vial chamber decomposition.
Right. Yeah.
And there's a sense in which one can understand the geometry of, so for example, prove that G bar is smooth by observing that T bar is smooth.
Mm.
So it's, there's a kind of, so it plays a fundamental role. So what's happening is basically that the other components of this are basically arise in a similar kind of way, just through some kind of vial group shift of a construction like this.
But the whole thing is connected?
No.
So
It's
each
got a
piece
bunch
is a
of
toric.
different, right, each piece is a toric
Oh.
variety. Some of them are points.
Uh-huh.
And so there's this big piece, which is T bar.
Right.
And then there are some other pieces. Some of them are points, but some of them are smaller dimensional toric varieties.
Like on the closed orbit, the two copies of the flag variety. There.
On the closed orbit, it's just the.
That's piece of this T bar.
No. If we take this and intersect it with the flag variety, what we get is the ZWW, where W is in the vial group.
Oh, sorry. Yeah, that's what, right.
But what happens is that then there are these other points that are fixed by T diagonal and G cross in the product of the flag varieties. And some of these points get linked together in this fixed point set.
Thank you. More questions or comments?
Can I ask a question?
Sure.
Hi, Sam.
Hi.
Yeah. Do you know how this T bar intersects with the coisotropic locus?
I think it has very small intersection. Sorry, go on.
Yeah, in particular, does it intersect the boundary?
Sorry, what boundary?
I mean the boundary of T. So T bar minus T.
I'm not sure what you're asking.
Sorry. So does the coisotropic locus intersect T bar minus T?
Oh, yeah. Sorry. Yes. So like there's a point Z. There's a point corresponding to the identity, which is T diagonal plus n comma n minus, and this is in T bar, and it's obviously and it's in T bar minus T, and it's coisotropic, which is straightforward. It's written as T diagonal is in G diagonal, and the other part is in G star. So there's that point. But I think yeah, and there should be other points. I haven't thought this through yet.
Okay, thank you.
Thank you. More questions or comments? All right. If not, Sam, thanks again for a nice talk. Well, thank you everybody for participating, and I'll see you next week. So the maybe an important point, if I remember correctly, how is it next week? It's on the Eastern Hemisphere schedule. Is it right? So which means it starts 3 hours earlier in your time.
So sorry. Who is speaking? I forgot.
Let me. Yeah, let's check. Sorry. Yeah, I should have been better prepared. Right.
Duan Yi Liao. I'm probably
Right.
mispronouncing that horribly. I apologize. The title is Homotopy Fiber Products of Manifolds.
Oh.
Thank you, Nikita. Right. So thank you again, and thank you, Sam. And
Okay, thank you. I'll see you.
See you next week.
Bye, everyone.